Hi everyone, can you hear me? Can you hear
Hi,
me?
Jingyi. Can you hear me?
It's low.
I hear you.
How about this? Is it loud?
It's good.
Yeah, it's fine.
Yeah,
Okay.
it's very loud.
How about Zoom people?
Jingyi,
Okay.
can you
So
hear me?
it seems like it's really low voice. Okay. Okay, I saw my head is green. Okay. I think we were going
It's
to
loud or not?
start at 7:15 to do a kind of a Zoom interview. So hi everyone, welcome to the post session of ES22. And I should say this is the first hybrid session we are hosting. So we are both doing in person and on Zoom. And so because it's kind of complicated, so that's what we are going to do. I'm going to show you here. So this is our setup. I was going to use this web camera to you to zoom in your face and also the details of your posters. And you will have a camera to introduce yourself to the Zoom people. If the Zoom people have any questions, they can just unmute themselves and talk to you directly by unmute themselves, do anything like doing a Zoom meeting. And I will use this microphone going to the broadcast their audio, so make all of us can hear them. So that's how it is going to be, and it's happening in like 8 minutes. If you find yourself like your number is larger than 20, you are going to be the first round to do the virtual Q&A. So just if you are larger than 20, you would be the second round. Happens at 8 p.m. So just we are taking around letting you know. Okay, that's all I want to say.
Wait, Jingyi,
Take your
can you
time
hear
to
me?
set up the stuff.
Jingyi, can you hear me?
It's
Amy.
You can just look here. It's all fine. It's all fine.
Jingyi? Jingyi? Jingyi, can you make me host? Okay, she can't. Okay, well, can anybody else hear me?
I can hear you.
Yes.
Oh, okay, great. Beatrice and Adiolu. Okay, great.
We can hear you.
Okay, terrific. I'm helping Jingyi, but I think she's very busy right now because she's running around doing, 10,000 things. So I just wanted to go ahead and make sure that, let's see. So I look at the posters. Does everybody know what she means by poster name? I'm going to put something in the chat. And so you can see, I think these are you see a link in the chat, and that's the number that she's talking about. So let's see, virtual presenters via Zoom. So I see Paul, Adebombo, and Surin, and Adiolu, Mahesh, Radhavan, Beatrice, Raphael, and hi there. Tashom, let's see, I don't know if Tashom is here. And then Diana, and then Jean-Baptiste, Shrejani, Safir, and Arpita. Yeah. So she has the rooms, let's see. Haley, Juan Ping, James Shepard, Camille, Pancha Kasan. Yes. So do you see an icon for breakout rooms at the bottom of your Zoom screen?
Yes.
Okay. So I think that's what she set up. I wanted to get a couple more details from her before, sending everybody out. But I'm okay. We had discussions about this. I feel it because there's about, what is it? 1, 2, like 5, 10, 15 of you. I personally would think it would be nice if just each person gave their presentation to this room of 15. But I don't know how you all feel about that. I'm kind of staging a coup over what Jingyi is doing. How do you all feel about that? If you would like to stay, because okay, so if you see the breakout rooms, then what happens is I feel like you won't hear some things. Oh, I guess somebody's putting people in rooms already. That's the thing. So Mahesh is in room 5 and Hongzhu is in room 1. How do you all feel about it? Could you let me know in the chat, or could you just, do you want, I feel like there's enough people to just stay in this room, this main Zoom room, and just everybody can hear everybody's posters, if that is reasonable. But if you want your own room and do what Jingyi said, that's also, of course, fine. What do you all think?
Hi, I'm Hongzhu. I exited the room 1, but somehow my head count is still there. I think what you said is a good idea.
You mean to have everybody just talk in this room together?
Yeah.
I think it would be nicer.
A small amount of people, right?
Yeah, I think it would be nicer.
Yes.
Anybody else have a feeling about it?
Yes, I think it is fine. Sometimes in the breakout rooms, you miss a lot, and then perhaps there is another poster or posters that you are interested in, and because you are hosting a breakout room, you will miss it. So I think this is a nice idea also.
Okay. Does anybody object? If you object, okay, so Dr. Giroux also, I don't think Dr. Giroux is presenting, but he is here. So he's an audience member, so he's willing to hear everybody's presentation. So that's what I would like to do, if that's okay. So I'm going to take a screen capture. Jingyi, can you hear me?
Yeah, I can
I'm
hear
waiting.
you. I'm actually broadcasting you to the whole audience.
Can you make me host?
Sorry? Oh,
Can you make me
I
a
need to
host?
get upstairs. So, do you mind to wait me for a few seconds and to go upstairs?
Okay.
Okay.
Yes. All right. So what I'll do is, I'm not presenting a poster. I think some of you know me. I know Beatrice knows me. Dr. Giroux knows me. At least E knows me. Paul Adibambo. We've had the pleasure of talking before. So what I'd like to do is, I'm just going to go down the list of the participants that I have. In my chat, I see 19 participants. So when Jingyi makes me a host, then I'm going to just run it like a workshop presentation. I'm going to pin whoever's going, and let's say, how much time does everybody want? Do we want, so we have 19, do we want to do like, is 3 minutes too short as a kind of overview? And then we can do the breakout room. Would that work?
I think it's fine that way.
Okay. All right.
Yes.
So I see 1 thumbs up, 2 thumbs up, and 1 verbal. It's not too bad. So, okay, that's what I'm going to do then.
Hi,
If that's
Amy.
all right.
I'm here. I'm on the second floor. I'm promoting you. Just 1 second.
Okay.
Did you see the make co-host message right now?
I see now I'm a co-host.
Okay.
And so what, Jingyi, I took a poll of the 19 participants here, and they would like to just have about 3 minutes per person to just give their poster to everybody in this room. So no breakout rooms, because then they will miss people.
Okay.
If
So
that's
then
okay.
we just don't use it. I would say it's.
Is that okay?
Yeah,
I'll
yeah,
just
that's
run
really
it up
okay.
here.
Yeah, I
Yeah,
should say that's
I'll just
okay.
run this up here. Okay. I said
but
up
I'm
here.
going to,
I'm not
like,
up where
broadcast
you are.
the audio. Just give me some seconds. I need to.
No, of course. Of course.
I need to
Okay.
turn on the audio.
Okay. So what I'm just gonna get ready, Jingyi. I'm just gonna get ready, okay? Okay, so everybody, that's what we're gonna do. And because my last name is Young, Y-O-U-N-G, I always have to go last in every single event. And I always feel very sad about that. So I'm starting at the bottom and I'm going to work up, because for now
Hi,
I'm in
everyone.
control.
Can you hear me?
Yes, Jingyi, we can hear you. Jingyi, we hear you. Okay. All right. I don't know if I'm gonna mute Jingyi. Okay, because now I'm co-host, so I can do whatever I want. Okay, so I'm going to take I'll make a screen capture of your names so I make sure I don't forget anybody. And then I'm just preparing this on my end. So let me see. Is Verena, the last person on my list is Verena. So Verena. Verena, are you giving a poster today? I don't see you on the poster list.
No, I'm not giving a poster today.
Okay, so then I'm going to move on to the next person on my list, starting from my bottom up. And that is going to be, let's see, who is next? Srijani, are you here? Yes, Srijani?
Yeah, hi, I'm here. Yeah.
Yes. Are you giving a poster today?
Yes, yes, yes.
Okay, great. So I'm going to ask you to camera, if that's all right. And I'm going to mute everybody but you. So at least while you're presenting.
So,
Yep.
do I
Mhm.
have to share the screen or like what you will be sharing it from whatever I have already, shared with others?
Oh, what would you like to do? Do you want to just show your do you want to show, I would say share it from your desk if you feel your internet can take that.
It's fine. And should I share the poster or should I share the slides that I have prepared? Which one will be good?
I would say slides. What do you think?
Yeah, yeah, it's good.
Okay. All right, and I'm going to set my timer. I'm going to get a little timer out just so that I roughly, hang on, let me ask my boyfriend to bring me a timer just a second. Okay. Okay, so let's see, Srijani, I'm going to put in 3 minutes here. And whenever you say you're, oh, Jingyi wants me to unmute her. Okay. It's very loud from her, but I'm going to unmute. Okay. Okay, so let's see. Yes. All right, Srijani, are you ready?
Yeah. I'll just.
Okay. Okay, so I'm going to let you share, right? So Srijani, when you're ready. Okay. And does everybody? Ah, perfect. Go ahead. And when you're ready, I'm going to put, everyone will get 3 minutes. I'm very, very democratic.
Sure.
Okay, you ready? Go.
It's visible.
Yes.
But I think there's a problem because, since I had to already send narrated slides, so I think slides are narrated. So yeah, I'll just take this. Okay, so hi, good evening. So this is Srijani Karmankar from IISER Tirupati, India. And today basically I'm going to discuss about my recent work where I have explored or rather proposed a new material GB3C2N3 for photocatalysis using hybrid TFT. So photocatalysis is basically a redox reaction which is driven by the energy of the solar photons, and hence the name. And for this purpose, 2D materials have been extremely beneficial because of the high surface area that provides. So we have more abundant sites, etc. And especially the 2D materials which are made up of boron, carbon, nitrogen are proven to be extremely promising because of the added advantage of high stability. And we are proposing basically a new 2D material in this class, which is, and we are going to explore the photocatalytic ability of this material. So we have performed the calculations using VAS, which as implemented, which implements TFT using projector augmented method and plane wave basis. And the structural optimization and stability analysis has been done with GGAPP, and the optoelectronic properties are explored with EHS06 function. So before we actually go to explore the photocatalytic ability, we first check the stability and the experimental realizability of the system itself, which I think is extremely essential. And we found that the formation energy is negative, and also there is no imaginary eigenvalue in the dynamical matrix. So basically the dynamical stability is also maintained and shows the elastic stability criteria is also maintained. Okay, so clearly the proposed system is experimentally realizable. And we find that it is a direct bandgap semiconductor with a bandgap value of 3.69 eV, which is greater than the net free energy change required for the photocatalytic reactions for hydrogen fuel generation. Also, it has a suitable band edge positions. The band alignment is such
Shrujani?
that the electrons from yes.
Oh, can you
Hello?
hear me? Somehow it's not forwarding your slides. At least it's not forwarding from me. What slide number are you on? I feel I still see your title slide.
Oh, okay.
What slide number are you on? Can you just recap?
Yeah, sure.
Okay.
I just
Okay.
check what is happening because I almost
Okay.
actually.
I stopped the timer. Okay.
Maybe I just do a fresh sharing. So,
Okay. I think so. I'm going to put a link in the chat to your poster, okay? So there we go. So everybody,
can you just see the entire screen? Is that
I see the Zoom meeting screen. I see your yeah, okay, great. So you're on your results, okay? Yeah.
Okay. So should I give a brief recap or should I?
Yeah, well, recap. Yeah, I think.
Okay. Hi, I'm really sorry for this inconvenience. Yeah. So basically, as I was saying that basically this is sort of an application of the advancement in electronic structure predictions, you can say. So we have used hybrid DFT to predict a new photocatalyst named GB3C2N3. So photocatalysis is basically a redox reaction where the redox reactions are driven by solar photons, the energy of the solar photons. And in this regard, 2D materials are extremely beneficial because of the high surface area they provide. Specifically, the ones that are made up of boron, carbon, and nitrogen are extremely promising because of the added advantage of high stability and this promising optoelectronic properties, etc. So we propose a new candidate in this base CN family based on hybrid DFT calculations and explore its photocatalytic ability. But before we actually go to that, let me just mention the methodologies. So we have used WASP to implement the DFT calculations, which implements DFT using projector augmented method and plane wave basis. For structural optimization and stability, we have used TGA-PB. And for accurate optoelectronic properties, we have used AGS06 function. And before the accurate calculation of photocatalytic ability, we have checked whether this system is experimentally realizable or not. At a negative value of formation energy, absence of any imaginary eigenvalues in the dynamical matrix, it shows that the basic stability criteria are maintained and basically the system is experimentally realizable. From the dispersion relation, we see that it is a direct bandgap semiconductor of 3.69 eV, which is greater than the net free energy change required for the water splitting and hydrogen production. And the band alignments are such that electrons from the conduction band can actually go to reduce H plus to H2, and the valence band holes can actually oxidize water. So the basic requirements of photocatalysis is maintained, and the harvested photons are near UV range. Now, since the absorbance is near UV range, the harvest of solar photon under the actual natural solar irradiation will be very low. So we tune it further by using biaxial strain, and we see that with compression, bands become more dispersive with wider bandgap, and just the opposite happens with expansion. And this reduced bandgap during expansion is actually manifested as a redshift in absorption spectra. So clearly, with expansion, we can actually achieve higher and higher number of solar photons. Whereas the work function actually shows a trend absolutely opposite to the bandgap, and as a combined effect of bandgap and work function variation, the band edges are realigned, and we see that the reducing ability increases with compression and the oxidizing ability increases with expansion. However, the photocatalytic ability is maintained almost throughout, through the entire strain range, and also for entire pH range, from absolutely from 0 to 14. So this clearly shows the robustness of the photocatalytic ability. That means even though there are some impurities or sacrificial reagents, the photocatalytic ability won't get disturbed. And we have a very good tuning ability using pH and biaxial strain. That is one extra added advantage that will give a good selectivity over the redox reactions. So these are my conclusions, that it can act as a near UV absorbing green photocatalyst, and this ability is maintained over pH range. Tensile strength provides the extra added advantage of redshifted absorption spectra and balanced HER-OER offsets, and precise control over redox reactions is achievable by varying pH and strength. So thank you. I request the interested audience to go through the references, and really thank you. Thanks a lot for your kind attention.
Okay, I'm going to mute Simons again. Thank you, Srijani.
Thank you so much. Thank you so much.
Thank you. Okay, very nice. I'm sorry to be so firm with the time, but I want to make sure everybody gets to go. Soren, I sent you a message in the chat. Are you ready to go? Soren, are you here?
Yes.
Oh. Okay, great. Will you be? Can you give your poster now?
Yes.
Okay, great. Then I'm going to go ahead when you get set up. So let's see. I think Srijani, if you can unshare, then Soren can jump in. Okay. There we go. Okay, so this is, I'm putting in everybody in the chat. This is Soren Adhikari. I hope I'm pronouncing that right, from the Indian Institute of Science Education and Research in Tirupati, India. Yes. Okay, great. Anti-ferromagnetic spin ordering and two-dimensional honeycomb lattice of SIP3.
Yes.
Okay, so there seems to be a problem with Zoom freezing on the slides. So when before you start, could we just I'll ask you to just scroll through slide 1, 2, 3, so they're not frozen. I don't know why Zoom is doing that, but they seem frozen in PowerPoint. So let's see. I see your title slide.
Yes.
I see your title slide, and then can you go to your next slide?
Yes.
Yes. Okay. Perfect. Yes. All right. Are you ready, Soren?
Yes, I am ready.
Okay. Okay, I'm going to start my timer and mute myself. So please go.
Okay. So hello everyone. So I'll discuss our recent publications. The title of the talk is Antiferromagnetic Spin Ordering in the Two-Dimensional Honeycomb Lattice of SiP3, which is basically a elemental substitution that like Si doped in the pristine blue phosphorin. So I will start with from the basic
recording in progress.
Graphene. So we are knowing that the graphene is a bipartite lattice, and I also have known that the graphene is showing the non-magnetic behavior. But due to this bipartiteness of this graphene lattice, we can induce the magnetism by creating H-like structure. So here is an example, the zigzag graphene nanoribbon. So if you see the non-magnetic band structure of the zigzag graphene nanoribbon, at the Fermi level, there is a exist of the flat band who is going to give you the diverging density of at the Fermi level. Due to that, the Fermi instability create in the system, and when you consider the magnetic calculation in the system, that will give you the antiferromagnetic coupling between the two edges. So now we come to the pristine blue phosphorin. So this is the crystal structure of the pristine blue phosphorin, and the looking of the band structure of the blue phosphorin, we can see. So there is a similar diverging density of states exist at below the Fermi level. So here our motivation to align this diverging density state to near or at the Fermi level. so which can bring the magnetism, as we have already seen in case of the zigzag graphene nanoribbon. Now, for doing that, so how to align this diverging density of state with the Fermi level? So here we have used the one the other 2D material called 2D BC3, which is the boron doped in the graphene, which also has been experimentally synthesized. So if you look to the band structure of the BC3, we can see the black line is the Fermi level of the graphene, and the dotted black line is the Fermi level of BC3. We can see around 2 electron volt is Fermi level is shifting. So we will use the same concept to bring the diverging density of state at the Fermi level. So here we the dope with the silicon that is the similar fashion like BC3. Now after that we have calculated the phonon spectra. So we can see there is no negative frequency pairs is there. So also is similar to the pristine band structure, pristine phonon structure of the blue phosphorine. So from this study we can say this SiP3 is dynamically stable and also can be experimentally synthesized. Now the look to the band structure of the SiP3. So it says there is a diverging density state just above the Fermi level. So although this calculation is the non-magnetic calculation, now if you consider the spin polarized calculation, so these bands are splitted and give rise to the magnetic ground state. Now we will see what is the spin structure of the SiP3. So if you see the silicon is connected through 3 phosphorus atom ferromagnetically, although the whole system is showing the antiferromagnetic ground state. So further we have seen that the charge transfer from the phosphorus to silicon, which gives rise to the local magnetic spin moment. So in conclusion, so we have theoretically proposed by using the first principle calculation the 2D magnetism with the form of the p block AL elements. And this is our reference, and I like to acknowledge this grants and thank you for kind attention.
Thank you, Soren. Thank you very much.
Yeah,
sorry,
you.
we're not going to take time for questions, but I know if you all hang out, and of course, I feel like it's always great to, just hear the person present. So our next presenter is Rafael, and let me find Rafael is from the University of California at Merced. So I'm going to put that in the chat. And Raphael's giving a poster, Excited State Forces in Organic Metal Halide Perovskites from GWBSD Calculations. I'm putting that title in there, and I'm also going to copy the link and put that in the chat. So that way. All right, so I'm going to mute myself. And all right, Raphael, thank you.
Okay, now can you hear me properly? And can you see the screen?
Yes.
Okay, thanks. So good night, everyone. For me, it's still afternoon here and at California, and I am Rafael. I'm from Brazil, and I'm working as a postdoctoral scholar at University of California with Professor David Strube. And our work is to study excited state force materials. So here I present some results for perovskites. And perovskites are materials that are being used for being studied to be used in solar cells. And one problem that people are facing is how to use them, how to keep its stability for some big period of time. So here, this work shows how is the degradation of this material that, for example, here the proportion of carbon atoms in some device is decreasing time. So our objective here is to understand the mechanism of how it's happening. So when we have a material and we excite it, for example, by absorbing light, the material goes from the ground state potential energy to excited state potential energy. So it is how the energy of the system changes with the coordinates. And when we go from the equilibrium structure from the ground state to the excited state, not necessarily the equilibrium arrangement of atoms the same. So the material face some forces that it goes to a new structure. And this is the deformation that appears. So for that, to understand that, we are using those excited state force that is the derivative of the excitation energy that is given by Bethe-Salpeter equations. And here are the expressions, so I will not spend time showing them, but they were developed 20 years ago from Ismail Begui and Louis. And we are developing a code that takes those results from Berkeley GW code and the quantum express, and then we calculate the excited states force. So here from some results in the right side of the poster, here are some forces for some extons on those states. And what we see is that the forces on the cation atom are bigger than the forces on the cage. And also analyzing the distribution of the forces, we see that the forces on the iodine atoms, they are sufficient to induce the migration of these iodide atoms, as we can compare here with this other theoretical result. So the conclusions are, we are developing this code, and with those forces, they are sufficient to make those migrations. And we see that those forces are bigger in the cations. And if you have more questions, I am glad to answer them. Thanks.
Thank you, Raphael. That was great. Our next presenter is, let me get the link up. Radovan. Radovan, can you unmute yourself? Let's hear your audio.
Yeah, sure. Greetings,
okay,
everybody.
Great. The audio. Hi, Radovan. Okay, so Radovan is concerned about sharing his screen because his internet might not be so stable. So what I'd like to do for Radovan's poster is to chat in the link, in the chat. I put a link directly to the PDF. I am going to share my screen. And so let me share my screen. So if you don't want to download the PDF, you can just look at my screen and follow along. And let's see. Oh, yeah. Okay. So Radovan, I think, right?
Yeah.
You can see my screen. Okay. So I know it's a little bit difficult because let's see, to fit everything in there. Maybe
it's a rather large poster, so
yeah. Okay. All right. But everybody should have a link to it. And I'm going to stop this. Okay. So Radovan is going to talk about exploring new phases in NIO binary system from ab initio. Great.
Thank you very much. I am a doctoral student at Slovak University of Technologies in Bratislava, Faculty of Material Science and Technology. And the aim of our work was the exploration of new nickel and oxygen binary phases. We have been focusing on viable stoichiometries that are currently not explored or only just poorly explored, namely the nickel sesquioxide oxide and nickel pentoxide. And we think that proper characterization of structure of these phases is a crucial starting point for the understanding of the relationship between their structure and properties. And since these structures are both not greatly described, our aim was to properly describe them. Our study was dedicated to theoretical prediction of crystal structure and properties related to the structure with the use of density functional theory and evolutionary algorithms. We have used DFT to evaluate the fitness of structure types that are common for transitional metal sesquioxide and pentoxide to accommodate the nickel and form a corresponding nickel oxide. And we have also used DFT in conjunction with the evolutionary algorithms to search for the global minimum structure. Basically, we present the analysis of found lowest energy structures for both nickel sesquioxide and nickel pentoxide, along with the analysis of geometry of the structure. We have also performed spin polarized calculations that have shown that both of these lowest energy structures appear to be ferromagnetic structures. We have performed electron density of states calculations that have shown that nickel pentoxide appears as a metallic conductor, while nickel sesquioxide only as a semiconductor. And the analysis performed done with the use of evolutionary algorithms was focused on the topology of the structures, their bonding networks, and the presence of oxygen bridges. Basically, nickel pentoxide, all of the structures or low energy structures from evolutionary algorithms that we have analyzed were containing the oxygen bridges, and we deemed that these structures and the oxygen bridges in these structures show that the potential of nickel pentoxide to be stable is with the use of large or high pressure due to the creation of oxygen bridges, since there were no oxygen bridges in the original structures. Basically, most of the information of our research can be found on the poster with, I think, much better explanation that I can give you right now, as it's fairly late here and I have a little bit of trouble focusing. But if there are any questions regarding our work, I will be happy to try to answer these questions. And thank you very much for your attention. And I hope that you will enjoy my poster.
Oh, sorry, I was muted. Sorry, thank you very much. Next, we have Mahesh Bawade, who's going to share the poster directly. All right. Mahesh, can you share your screen? And then for everybody, I'm going to post the link, the URL as well.
See my screen?
Yes.
Yes, you can.
Okay, and then to everybody, here's the PDF link. Okay, so you can either download it, look at it locally, or look at Mahesh's shared screen.
Okay. Okay. Everybody can hear me, right?
You sound good.
Yeah. Okay. Good evening. Myself, Mahesh Balwade. I work with Professor Prabhakar Singh at the Indian Institute of Technology, Mumbai, India. My title of the poster is Theoretical Study of Electronic Structure of SN4G using First Principles. It was recently predicted that tetramer structure of germanium-5 and tin-5 as a topological semi-metal and topological insulator respectively using first principle calculations. As the germanium tin both have same valency, it is likely to have similar topological properties in the tetragonal allotropies of compound made up of germanium and tin. Hence, we studied the electronic properties of SN4G. The main aim of this work is to study electronic properties of SN4G. We study its formation energy to check this stability. As we know that germanium tin as a heavy element, hence we also include a spin-orbit interaction while calculating its band structure and density of state. Geometric optimization and self-constraint calculation are performed using density functional theory as implemented in a contact express zone. We have used a projected augmented wave pseudopotential with PB exchange correlation functional. In the figure 1, as you can see, we have shown here a fully optimized structure of tin for germanium, and its space group is P4 bar M2. And we calculate the formation is minus 4.17 electron volt. Hence, it's a chemically stable one. In figure 2, we have shown Brillouin zone with the high symmetry points. In the figure 3, we have shown here band structure. As you can see that it is a metallic one. In the figure 4, we have plotted band structure with including spin-orbit interaction. As you can see that in the path of M to gamma, significant band structure splitting is found. In the figure 5, we have plotted total density of state with and without spin interaction, as well as we have plotted tin 5p orbital contribution as well as germanium 4p contribution in the figure 5. And as you can see that in the total density of state, spin orbit interaction doesn't play any significant role because there is no significant change. And cyan color show the tin 5p contribution, and the blue color show germanium 4p contribution. And you can see there is a strong hybridization between -4 to -2 electron volt. And we have done spin polarized calculation, confirm the non-magnetic nature of SN4GE. And we also plotted the Fermi surface in the figure 6. The left panel of figure show typical Dirac cone with the gap. We are interested to know the reason of this typical Fermi surface. We are working on that. In the table 1, we have shown the lattice parameter and bond length compared to the Germany 5 and tin 5. The data is taken from the reference one for Germany 5 and tin 5. As you can think that Germany has less atomic radius compared to tin. Hence, its a lattice parameter A and C is less compared to tin 5 and more than the germanium 5. We also shown here the bond length for comparison. Hence, in the summary, we have studied the ground state of newly projected tin for germanium, which is found to metallic and non-magnetic in nature. The inclusion of spin orbit interaction gives the significant band splitting along M to gamma path. And we also found that that typical Dirac cone in the Fermi surface plot at a gamma point. And thank you for listening. And this is my closing it.
Thank you, Mahesh. That was great.
Okay, I will stop my sharing.
Thank you. Perfect. Okay, so let's see. The person who is next on my list is Camille. I sent Camille a chat. Tokar, are you there?
Yes, I'm here.
Okay, would you like to give your poster?
Yes, I would.
Okay. All right, so let me post that. Okay. So I'm putting it in the chat. This is poster, oh, I missed the one. It's actually poster number 18. And this is, am I pronouncing your last name right, Tokar?
Yes, that's correct.
Okay.
That sounds correct.
Okay, good. Charge ordering mechanism in silver difluoride from first principles. And do you want to share your screen or do you want me to share a screen?
I would like to ask you to share the PDF of the poster on the
Perfect.
screen.
All right. So I'm also putting the PDF in the chat for everybody who would like to just download it locally, but I'm going to share my screen. And let's see. Yeah. Can you see that? Let me zoom in a bit.
Yeah.
Let me keep going.
Okay.
So you just tell me when you want me to, scooch down and so forth, right? So let me.
Now it looks fine.
Okay, so I'm going to start at the top and you tell me when to go down. Okay?
Okay.
All right.
Maybe.
All right, I'm going to start the timer. I'm actually a little bit generous because I want you all to have enough time. But everybody's been so good about keeping within 3.5 minutes. So I'm still using the timer though. Okay. Thank you so much, Camille.
Yeah, thank you. So I now can start. Hello, I'm Kamil Tokar from Advanced Technology Research Institute at the Slovak University of Technology. Recently, it was demonstrated that the common alpha phase silver difluoride structure represents an excellent silver analog of the parent compound of high temperature superconducting cuprates. Reported observations indicate that the charge-ordered alpha phase may be stabilized already in an undoped regime in contrast to the superconducting copper oxides. Charge-ordered phase is metastable relative to the spin-order antiferromagnetic phase and could be quickly destroyed thermally via intervalence charge transfer. The existence of the beta mixed valence phase and its transformation to alpha phase clearly points to competing AFM and charge density wave orders with different mechanisms of electron localization in silver difluoride. In our work, we mainly focused on investigation of the mechanisms underlying charge ordering in alpha phase concerned with electron-phonon coupling and its possible relation to the Kohn anomaly and Fermi surface nesting based on non-hybrid density functional theory technique and first principles simulation of the phonon system. We shown by generalized gradient approximation calculations how soft phonon molds with the presence of Kohn anomaly promote commensurate and incommensurate charge density wave orderings in the metallic case at reduced temperature and electronic correlations. The existence of possible nesting vector that is connecting Fermi surface areas of the corner pockets around the R points of Brillouin zone can support the formation mechanism of charge density wave regime in this silver difluoride. From the electronic E-doses analysis, we shown that the soft phonon molds can act simultaneously in formation of Ag1 plus and Ag3 plus sites within the crystal structure, and the full charge transfer takes place at Hubbard's Coulomb local iterations. The phonon-driven mechanisms of electron localization might compete with the antiferromagnetic interactions and this way promote charge disproportionation in the alpha phase. Simply saying, in the conclusion, we uncovered CDW mechanisms underneath the AFM spin ordering. We shown the existence of soft phonon mode related to the Kohn anomaly, which is enhanced by Fermi surface nesting. And also there is possibility of tuning the electronic properties between the charge orderings and spin orderings regime, for example, by strain or alloying. And thank you for your attention, and feel free the further details in the poster. Thank you, everybody.
Thank you very much. Let's see. Oh, Hongju is present, but he's actually not presenting a poster. Okay, so next then on my list is Diana. Diana?
Yes.
Would you like to present tonight?
Yes.
Okay,
I will
great.
share my screen.
Okay, I'm going to put in the chat your name, and I'm going to also put in a link to the APAM site. Okay, but you can download. Do you say Diana or Diana?
Diana.
Diana's poster from the link in the chat, and then I'm going to clear this. Okay, I'm going to mute myself. Thank you, Diana.
Okay, thanks. So my name is Diana Fabushova, and I'm the master student at Slovak University of Technology in Bratislava at Faculty of Material Science and Technology. The title of our study is Initio study of impact of pressure and temperature on stability and polymorphism of palladium dioxide. Palladium and its oxides are important catalysts in many catalytic reactions with diversity of technological applications. The only fairly scientifically studied and technologically exploited palladium oxide is palladium monoxide. Formation of one palladium dioxide polymorph was observed under elevated hydrostatic pressure and temperature, and rutile structure was proposed. So in our study, we focus on theoretical prediction of stable palladium dioxide polymorphs and impact of pressure and temperature on their stability using density functional theory modeling. First, we modeled palladium dioxide in 19 crystal structures observed for dioxides of transition metals, but only 13 models behave as stable in respect to palladium monoxide. All palladium dioxide models were optimized under pressure in a range from 0 to 100 kilobar. The lowest energy structure at zero pressure is predicted to manganese dioxide type at hybrid GFT level and vanadium dioxide type at standard GFT. Both standard and hybrid GFT predict orthorhombic rutile type structure to be preferred at elevated pressure. We also perform first principles calculation of lattice dynamics for rutile type structure. And we found out that tetragonal rutile structure is dynamically unstable, but orthorhombic rutile structure is dynamically stable. We also found out that the increasing of the electronic temperature via smearing stabilizes tetragonal rutile structure. So thank you for your attention, and for more details you can see in our poster.
Thank you, Diana. That was really great. Nice. Okay, so next is, let's see, Adeolu, are you ready to go?
Yeah, I'm ready to go.
Okay, or are you ready to go to sleep? Sleep. Okay, can you share your screen?
Okay,
or do you
sure,
want
yeah.
me to do it? I can do it or you can do it. Okay.
Give me some.
Okay, and Paul Adibambo, what time is it for you there? I should have taken that into account.
Do you want me to show poster or the?
Okay.
Sorry, I heard by name. I don't know.
What time is it for you, Paul Adibambo?
Oh, this 1 a.m. 12:58 a.m.
Okay, so I have you coming up in 2 posters. Is that okay?
Okay.
Okay. All right. Thank you. Okay. So, all right, then go ahead, Adeolu. I'm going to clear this and then, yep. And then we'll be Beatrice and then Paul. I hope that's all right for everybody. And I'm going to mute myself. Oh, so, oh, great. Thanks, Beatrice. Let's see. Adeolu, I don't see your screen. Can you share?
Okay.
Or?
Can you see it now?
You see it? I don't see it.
Okay, no problem.
Okay, let me try again. Okay, view poster. And here's a direct link to Adeolu's poster in the chat. Okay, great. And now we see it.
Can you see my screen now?
I see it's, yeah, I see your phone. Perfect.
Yeah.
Okay.
It's very dark here and there's no light.
Oh, okay. Can you make it a little bit bigger? Yeah, that looks good.
Can you see it now?
Yes, that looks good. Okay, so I'm going to mute myself and thank you.
Yeah. Hello, everyone. I am Ayola Diolu from University of Ibadan, Nigeria. The topic of my presentation is formulation of a new exchange correlation functional for better band gaps in density functional theory. The total energy of any system consists of 2 parts, the known and the unknown part. The unknown part is called the exchange correlation energy. And it is the part that is responsible for the prediction of materials. But the actual mathematical form of this exchange correlation energy is not known. Therefore, approximations are made for it in density functional theory. So in this work, we formulated an exchange correlation functional, which is the modification of Anken and Sham functional formulated in 1988 as given in equation 1. Can you see my screen? So the new exchange correlational functional that we formulated is shown in equation 3, and the modification that we did to the Anken and Sham functional is in the term inside the bracket, the empirical parameter C before the EP. The functional were optimized for different values of UI alpha. The time inside the square bracket is time as UI alpha, and the functional was optimized for different values of UI alpha in order to get the average CEP pair, the energy gap. And also the CEP pair was made the subject of the formula in order to get the analytical part for the CEP. Then we now use the CEP pair and the CEP analytic. We plot the two on the same graph against the UI alpha, and we obtain the optimal values of UI alpha. The intersection of the two curves as shown in this curve give us the optimal UI alpha, which we use to run our band structure calculation. Yeah, this one is the band structure calculation that we did using our functional. Here we have gotten an energy gap of 1.2 for silicon. And the second one here now is the band structure that we got from LDA method, where we have gotten the energy gap to be 0.59. So this is the table of our result. So the experimental values are this. Then we have the energy gap that we got from a LDA method at this. Then X alpha at the energy gap that we got from our functional. As we can see that our energy gaps are better than that of LDA method. Therefore, as shown in the table, the experimental value for silicon is 1.17, where we got 1.10 EV, while that of LDA gives 0.47. For silicon carbide, the true value is 2.40 EV, and we obtain 2.27 electron volt, more accurate than that of LDA, which is 1.35 electron volt, and so on. Therefore, a major setback in DFT approach has been partially overcome by our method. These are the references that we consider in our work. Thanks for listening.
Thank you, Adeolu. That was great. I would like to also mention to you before you take off, and some of the others, if you're just coming in, we're running a slightly different style. So I know that James is new here, and with the group, I'm just going down the list in order. And also, Adeolu, did you attend our US AFRI workshop last week?
I did not.
Okay,
I received it late.
Okay, no problem. So for the whole group, I'd just like to tell you that Andre Schleifer, who's a University of Illinois at Urbana professor, is an editor for a special edition of an special issue on electronic structure from IOP. So that's something that's coming up, and it's I think they're going to have fee waivers for different countries for submitting papers. So some of you might be of interest in that special issue, and so I'm going to put my email address in the chat, and so please just email me at either of these, Africa Initiative at gmail.com. Yep. So email me at either of those things, and then that way I can send you a little bit more information, things that we discussed at last week's workshop. So that's one thing. Also, there will be probably another data workshop for the materials at Berkeley National Lab. That'll be run by Matt Horton and just to give you some updates about that. And so they haven't decided yet if they're going to run it, but if they do, they might be able to run some fee waivers for that as well. So that's working with the materials project. Let me just put that in the chat real quick. So I know it's late for some of you, but I just wanted to mention these things because I think it's of interest, and it's not clear to me that you might have heard about it in any other way. So this is a link for the materials project at LBL. And they are, I think they might run another summer school on their project. And so if you're interested, you can also just email them. And the person to contact for that, he's running it, is Matt Horton. And he spoke last week at our workshop last week about that they're still thinking about the summer school, still trying to work it out. Okay, so those are just things I think all of you are probably interested in. Oh, let me put Andre's name in here. So I'm sorry to interrupt with everything. So he's at University of Illinois at Urbana-Champaign. That's my school. So if you want to talk to him and you're like, what was his contact again? And so that's the special issue. And that related to the US Afri Initiative, and that was the workshop, and then the visit, and that's electronic structure. And he mentioned fee waivers for some countries. So let me just get Andre's email address. I hope this is useful. I don't want to derail the schedule, but I just want to make sure that you all know these things. I think they are good opportunities for you. Yeah.
Okay.
And so let's see. That's his email address.
Okay.
Okay, so just contact if the special issue sounds at all of interest. It's really focused on electronic structure and with a focus on our US Africa initiative. And also there's some other summer schools and some other workshops that are coming up. So contact me if, I know more than this. So contact me if you're at all interested in these things. I'll have some other slides to inform you about. Okay, so alrighty. So next up is Beatrice. So Adeolu, if you're ready, we'll turn the screen over to Beatrice, and then we'll turn it over to Paul Adebambo, if that's all right.
Thank you.
Thank you. Thank you so much. Okay, so Beatrice, I'm going to put out a link to your. Do you want to give your slides, or do you want to have people look at your poster?
No, I will share my slides here. Can you see it?
Yes, it looks great.
Yeah,
So let's
sure.
practice. Let's practice. Going forward and backward.
Yeah, sure.
Perfect. I see the who are. Okay, that looks great. All right.
Thank you.
So this is Beatrice Cogolo at the University of Cartagena, and I just put in the chat direct link to her PDF, which she uploaded just for easy reference.
Thank you. So
Okay.
much. Yeah.
All
Okay,
right.
so-
Let me clear that.
Super. So my name is Beatriz. I'm working as a postdoc researcher at the University of Cartagena, which you can see there in the slide. So my work is about fluorine, and the thing about it is that in the past couple of years, there were a couple of papers where they were studying fluorine at very high pressure, so in the terapascal regime. Although they were they published some results, there is some controversy regarding the phases, regarding the transition pressures. So what we want to do is to perform another structural search using a more unbiased method, because the other two groups use some biased methods for proposing new structures. So what we have done so far, because this work is very early stages, is that we use specs with different size cells from 2 up to 16 atoms per cell, and we run these calculations at different pressures, starting at 1 TPa, 1 terapascal, up to 5 terapascals. And the energies were calculated using Quantum Espresso, and so far we obtained nearly 29,000 structures to analyze. So after that, we found these 12 structures as some proposals that we found so far, and then compared to the reference that were already published in the past couple of years. And we performed some refined calculation to see whether if the symmetry remained or not. So after that, we found that from the references, only the CMCA phase survived, and for our research results, 7 structures remain. So what we did then was to compare our structures, varying the number of atoms per cell against the reference that survived, and we found that for 2 atoms per cell, all the 3 structures found at some point they become more stable than the reference. For the case of 4 atoms per cell, is nearly there, almost at 5 terapascal, but still is a bit. They have a bit of energy higher than the reference. The same thing happened with the structure with 6 atoms per cell, and with the structures that we found with 4 atoms per cell, we found the reference that is used against the others, and another one that at some point becomes more stable. So what's next? So the next thing is to perform some phonon calculations and include temperature contributions in order to construct a phase diagram, in order to obtain a more realistic picture of how fluorine behaves at not only very, very high pressures, but also at high temperatures, because that's the combination that you will find in nature when you are under these very extreme conditions. So thank you so much for your attention, and this is my email, and then you have the posters, so, and also a video with these slides. So thank you so much for listening.
Thank you, Beatrice. That was great.
Thank you.
Thank you. Okay, so next up is Paul. It is also 1 a.m. for him. Yes, so this is, let me put this in the chat. Okay, so Paul, you can go ahead and start sharing. This is the Paul Adibambo. He's going to talk about Hofheusler alloys. And Paul, are you ready?
Yes, I'm ready. I've tried to share my screen. Yeah.
Okay, great. Okay, I'm going to put in the chat a link to your poster file, and you can go whenever you're ready.
All right. Good day, everybody. My name is Paul Adibambo. I am a lecturer from Federal University of Agriculture, Abeokuta, Nigeria. I will be talking about assessing the thermoelectric properties of platinum, scandium, and bismuth Hofheusler alloy. The Hofheusler alloy is divided into 2 types. We have the full Hofheusler type and the half Hofheusler type. The full Hofheusler type has a general formula of A substitute 2 BC, while the half Hofheusler type has a general formula of ABC. In both cases, A and B elements are transition metals, while C is semiconductor element or SP element. And our primary objective is to have a material with narrow band gap and very low thermal conductivity. And the motivation of this work has to do with various usefulness of Hofheusler material, which are among optoelectronics. We use them in shape memory, micro electromechanical system, and thermoelectric properties. And the search for new materials to meet global energy challenges has motivated us to study this Hofheusler alloy. And the method of computation has to do with the combination of density functional theory with some other methods. And in particular, we calculated the lattice thermal conductivity of this material, Thereafter, the electrical conductivity was calculated using equation 2, and the power factor, which depends on the Seebeck coefficient, as well as electrical conductivity, was calculated using equation 3. And the crystal structure is shown in figure 1a, and we can see that the bismuth alloy is sitting at the edge, while the scandium alloy is in between the bismuth alloy, and which is at 0.05, 0.05 lattice. And the lattice constants of this crystal alloy is calculated to be 6.42, as shown in the parabolic curve here. Had the band structure, as well as the density of states, is plotted, and we can see the narrow band gap of about 0.31 electron volts, as displayed in figure 2, while the phonon dispersion curve is presented in figure 3, and we can see that this is divided into two regions. We have the acoustic mode and the optical mode, and the absence of negative frequency tells us that the material is dynamically stable. And the lattice thermal conductivity is plotted in figure 4, and we can see from 400, at temperature above 400 Kelvin, the lattice thermal conductivity of this material appears to be very low. And the thermoelectric properties, which has to do with the power factor, the electrical conductivity, and the Seebeck coefficient, are tabulated in figure 5. And here we can see from the power factor result that it's the higher the temperature, the higher the power factor, while the Seebeck coefficient curve tells us that in both the P and N-type material, the minimum and maximum value occurs at the room temperature, which is at 300 Kelvin, and the figure of merit of this half-Osler alloy is tabulated in figure 6. And we can there is room for improvement on this particular result. But if you have any further question concerning this work, I will be glad if you can contact me immediately after this session so that we can discuss together. Thank you for listening.
Thank you so much, Paul. That was really great. And I must say, I feel I really learned about Hofhäusler alloys from you, from 2019, from your presentation in 2019. So I have a better understanding of that. Perfect. Okay, next up is, let's see, Safer, right? Am I pronouncing that correctly? Safer Bora?
Yes, Safer.
Safer, okay, a little bit faster. Safer, okay. And let's see. So you said your internet is good. So let's go ahead and look at your slides. Perfect. Okay, let's see.
Okay. Hello, everyone. Hello from Turkey. It is 3 a.m. here.
Oh my gosh, I'm sorry. You win the prize. Okay, thank you, Safer.
I simply talk about a software that we developed for the last year. So I already upload a video about it. However, I want to talk a little bit at here. What's the problem here? The problem, if you want to use GPO, DFT software for your studies, you need to use ASE and the GPO in Python, and you need to write your ad hoc scripts. And because it is very hard to write each and every time your script, we developed a software called the GPO tools. And here we have two main Python scripts here, GPO Sol and GG. Let me show you when you, sorry, when you download GPO tools from this website, and there are some easy installation terms here. And even you can install it with Conda. I already use in a Turkey's HPC system, Turba, with a Conda installation. So let me show you a very easy example. So when you install it, you had a, this is a Windows 11 system, by the way. Let me show you. Let's go to example folder, and there is a silicon 2-atom example here. Let me quickly do it for you. I already ran it, of course. Where is it? Yep. So with a easy example, let me show it to you. It's a 2-atom example, so it will finish right away. Yeah, so it's finished. So let's go to the results folder, and everything is here. If you want, you can also we also write a GUI for it. So you can run it, same thing, same things here. You can write your input parameters here, and then run from here, and at last you will get the structure and those figures. So it is not an application of DFT for this presentation. However, please give it a chance, and you may give it to your students. I already doing like that. And both ASE, GPO, and our software is open source and free software, so you can easily use it for your studies like that. So I hope you enjoy. That's the end of my presentation. So also you can send your issues when you use in our GitHub repository. So just go to our website and enjoy using it. Thank you very much for listening.
Thanks, Zafer. That was great. I put in the chat links to your poster and links to your lrgresearch.org gpause-tools, so people can access it there. Thank you. All right, terrific. I also took a screen capture. I'll probably insert your face into some Zoom Zoom group photo that I'm making. Okay, so it's 3 a.m. I will let you rest now. So next up is James Shepard from the University of Iowa. And I'm going to share the poster from my screen, and I put in the chat this link that I'm sharing with you in case you just like to download it locally. And then let me share this here, and I'm going to zoom in a touch more. How's that? A little more, or is that good?
That looks good.
Okay, all righty. So this is James Shepard from the University of Iowa, and I'm going to mute myself.
Awesome. Hi, everyone. So as Amy said, I'm James Shepard, and I'm an assistant professor at the University of Iowa. This poster is about work that I'm doing with a graduate student called Will van Benschoten, where we're aiming to continue the development of a quantum Monte Carlo method, which calculates finite temperature electronic energies. The other methods that you might have heard of that already do this include density functional theory with smearing, auxiliary field quantum Monte Carlo, or path integral Monte Carlo. Our method is called piecewise density matrix quantum Monte Carlo, or PIP DMQMC, and this is implemented in the Handy software package. PIP DMQMC is different from these other methods because it uses a basis set similar to full configuration interaction or exact diagonalization, and its aim is to achieve exact on average accuracy. In DMQMC methods, an exact and well-defined starting point is required. And so this could be, for instance, the high temperature density matrix, which is the identity matrix in any basis, or alternatively, the exact mean field density matrix. When you start with the mean field density matrix, you get a calculation of one temperature at a time, but it's easier than starting from the identity matrix, especially for very large beta or very low temperatures. But the calculation nonetheless reaches an exact density matrix at this temperature. What we realized in this contribution is that it was possible to switch the propagator at the end of the simulation and use something called the Bloch equation to continue the propagation once you've gotten the exact density matrix. Once this is done, you can get all of the temperatures past the switching temperature from one calculation rather than having to do one temperature point at a time. This is a considerable improvement. The results shown in the poster are a highlight of the validation figures for this work, and this work is now published in the Journal of Chemical Physics, and I'd encourage you to look at the poster or our paper if this sounds interesting to you. Our long-term aim is to improve the scaling of our method and study phase transitions in solids. And this work is funded by the Department of Energy. I'd like to thank them and also Amy for organizing this session. Thank you, everyone.
Thanks, James. I feel organized. Let's put that in quotes. This was kind of an ad hoc thing. I just want everybody to get a chance to talk. I feel like you've all spent time making your posters and your videos, and so I want you all to share your research. Okay, next up we have Arpita. Let's see. I think Arpita, are you ready? Yes. So James, I'm going to stop sharing your poster now, if that's okay, and so Arpita can share her screen.
Yeah, I'll do that.
Great. Okay, and so while Arpita is queuing up her poster, if you are here and you did not go yet, please tell me in the chat so that you can go after Arpita. And I see, because I see a couple of names, but I've checked in with everybody I think who wants to present tonight. So if I don't get any further chats, Arpita, you are our grand finale poster for tonight. Okay, all right, I'm going to stop and mute myself.
Okay, so my talk is first principle study on structural, electronic and magnetic properties of bilayer trigonal vanadium selenide and cobalt heterostructure. So I'm basically working with Dr. Tushar Rana in the Department of Physics and Nanotechnology. So basically, what is the main motivation of the work? So transition metal dichalcogenides, they have their van der Waals layered structures, and they basically span a great part. Like they can be seen as a semiconductor, they can be seen as metallic structures. So what do we have here? So here we are taking a typical transition metal material. So basically vanadium is sandwiched between two selenium atoms and we are stacking it along 001 direction. So we have considered here the trigonal phase. So as Richard Feynman has said that there is a plenty of room at the bottom. So we just want to explore that how these layered structures actually work, what we can do exactly with the correct layers. So can we even apply them? So can we tune them? So with this research questions, we have started this research objective in which we have checked the magnetic properties of this layered structure, and we have checked the influence of the Hubbard U parameter, and then we have also incorporated the correction along with it. Now this figure, as we can see here, so the figure shows the top view and side view of the material along with the along what we have taken with cobalt. Now why specifically we have taken cobalt? Because iron vanadium interfaces have been already studied. So we have tried to do and we have tried to see what is the effect if we take some other ferromagnetic substances. So we have modeled it in such a way so that we can take the T phase, and U parameter has been taken as 3 electron volt. So we have actually varied the U parameters in different ways, and we have found out, that's why I have taken the 3 electron volt here. So we have taken I have used the VASP for calculation. So we can see the figures. Now basically what happens, what we can conclude that Now this basically is a demonstration of contamination-free interface, and we can say that through interfacial hybridization, if we take the cobalt overlay, the magnetic moment of vanadium selenide was increased. And so what is basically happening here? So we can see here there is a shift in the cobalt peaks. So the vanadium 3D is less than half filled, and it's favoring antiferromagnetic coupling. So that is in reducing the magnetic moment of cobalt, and this is how we can treat the vanadium iron cobalt interfaces. And further what we can do, we can also study the different phase. We can take the hexagonal phase. This particularly has a space group of P3 bar M1, that is trigonal phase, but we can also check the hexagonal phase. We can also check the different stacking orders, and we can check the variation by increasing the layers and successions, and we can also find the relative state. So I'm working on that currently, and these are my references. So thank you for your attention.
Thank you, Arpita. That was great. Very nice. Okay, so our next presenter is Juan Ping from UC Santa Cruz. I think Juan is here.
Hello. Yes,
Hi there.
Hi, Amy.
Okay, let's see. So do you want to share your screen? Your internet is feeling strong?
I can share from my side.
Okay, perfect.
Okay.
I'm going to mute myself, and I'm going to put in chat links to Juan Ping's poster. Okay, great. Go ahead.
Thank you, everyone. This is Yuan. I was going to give a talk in the workshop, but at the end we couldn't make it. Anyway, so I'm going to introduce this poster. So it's an overview of the recent work in my group. So the first 3 panel is about the study of quantum defects in quantum information science. So let me just zoom in a bit. Theoretically, we want to design defects which could be useful and promising for single photon emitters or spin qubit. Then they need to have the list of properties. For example, they have to have deep levels and bright optical transitions, high spin state, high quantum yield, and PL contrast, and long spin relaxation coherence time. In order to compute all these properties reliably for defects, in particular in 2D materials, there are quite a bit of interest in recent years from experiments. We need to develop new methodology, as I listed here, because in 2D materials, there's a strong electron correlation, and there we need to use a level of like GW approximation or above to describe electron correlation. And there's a strong electron hole interaction, then we need to solve the Peters equation to get optical properties with excitonic effect. And in fact, in the experiment, there's always a substrate below the 2D material. Then we develop a theory to include substrate screening. One, we have to look at the defect properties. And in addition, the defects can be charged, and the method to properly describe or correct the spurious charge interaction in charge defect needs to be developed. And this is part of our recent development as well for 2D system. At the end, we also develop a theory for spin relaxation time. This will be the lower panel. So as example, I show you what we can do as example of the carbon defects in HBN. There has been experiments showing the carbon defects could be the 2eV single photon emitter candidate. And then we explored a few carbon defects and we find the C2CN has the best agreement on several properties. First, the photoluminance PL lifetime. This included the radiative lifetime and the non-radiative lifetime, which is through the phonon-assisted recombination. And we computed the PL lifetime, which is the red dot, and it's in the range of experiment without the blue dots. And then we compute the Huang risk factor. Huang risk factor is description of the strength of electron phonon coupling. which is also compared in the range of experiment. And this is the diagram of the energy landscape of this CN with excited state and two different excited state and the ground state and the different process. What we find, the parameter computed here agree with the experiment fairly well. In particular, the PL line shape also agree with the experiment very well. So this is a way to identify defect. We have to compute multiple parameters in order to confirm the chemical composition. And as I mentioned, for the different process, for example, radiative recombination, we have to include the fact optically there is a strong electron-hole interaction in 2D material, for example, HBN, and we solve the Bethe-Speeder equation, compute the exciton dipole moment, and then we can obtain the exciton recombination rate. And the non-radiative process will compute electron-phonon coupling. We show an example how the electron-phonon coupling, which related to the lifetime, non-radiative lifetime change as a function of strain. At the end, you need to worry about intersystem crossing between triplet and singlet, because this process is the key step to generate imbalance of the different spin state or spin state initialization, and it's required for spin readout as well. So we compute this intersystem crossing, including spin orbit and the electron-phonon coupling. So more details you can find in our recent work in this reference 10 that was listed down in the reference panel. So another thread of the research is on the ab initio density matrix dynamics. This is brand new research theory development, including implementation. We're evolving the density matrix role in real time, and we include coherent dynamics and incoherent dynamics in the framework of quantum master equation, in particular with Lindblad dynamics. There in the coherent dynamics, you have light matter interaction and external B and electric field. And in coherent dynamics, you can have electron-electron, electron-impurity, electron-phonon interactions, which we have implemented entirely from first principle. As example, in the incoherent part, we have this scattering term written in such way contains the scattering matrix P. And this P, if you zoom in, look at this is example for electron-phonon scattering. We include the electron-phonon matrix element G with a spin-orbit coupling. And this will be a fundamental element to compute the scattering matrix. So with this framework, we can compute the carrier and the spin relaxation. And spin relaxation can be extracted from this trace of rho and the spin operator. And this decay gives you the spin lifetime. In this framework, the nicest thing, we can include all the different contributions. We can also identify which contribution is most important under different temperature and carrier concentration. So this is the example I show you with such theory. It's fully general. We have tried a different system, for example, 2D materials and 3D materials. So these are two examples on 2D materials. One is graphene on HBN, another one is silicon Germany. We also have recent work on these two materials on substrate. So here is example. In the past, when you look at spin relaxation and interface, it's always difficult, especially to do in model Hamiltonian. It's difficult to parameterize the model Hamiltonian. And we do not need to generate model with any input. We do not need any input parameters. So with the first principle calculation of different scattering process, we can identify at a different substrate what will be the spin lifetime, for example. So graphene standalone is the highest at 10 to order 6 picosecond. When you have electric field, it lower several order, and with HBN, again, lower the several order. And this HBN substrate cause an anisotropy between the in-plane and out-of-plane dependent on applied electric field. This has not been reproduced in the past in the past theory, and we reproduced this behavior larger than 0.5 first time from our first principle density metric dynamics. And more importantly, we can predict the system with a large long spin lifetime and long diffusion length as example of Germany. We show in this system, it has this spin completely out of plane. This is its spin texture due to strong spin orbit coupling. And it shows the spin valley locking effect at a low temperature. And more importantly, we show this spin lifetime can be tens of nanoseconds, even longer than graphene. And in particular, this spin diffusion length can be tens or 100 micrometer. This is very good performance, considering we also consider the effect of impurity at the finite temperature. So we show you we have a tool can give you useful predictions and interpretation of experiments. And beyond the 2D system, we can also apply to the 3D system of cesium lead bromide. This is the work we haven't published yet. We first time computed a spin lifetime for cesium lead bromide as a function of temperature. And we also included the carrier density in experiment. We compare with experiment very well. And down below shows the importance of impurity. So cesium interstitial give an important effect on the low temperature range. So the low temperature agree with the experiment much better if you include the defect. More importantly, experiment they like to look how it responds to magnetic field. This is something we developed recently. We need to compute. So in the G factor, you need to contain the orbital part and the spin part. And the orbital part in particular need to be implemented in a way compatible with periodic boundary condition. That's more detailed formalism. We are having a paper under preparation. So that's about the work. The perovskite is a big field. Their spin lifetime, spin relaxation is very interesting because it's very tunable with different symmetry and spin orbit splitting. That's something we are actively working on. Okay, so the work is supported by Air Force and the National Science Foundation. Thank you.
Thank you, Wanping. That was great. Put links to her poster, her group's poster in the chat. And for those of you who would like to, I'll ask you to turn on your camera so that I can see you. And I'm going to take a Zoom group photo and I'm going to somehow get it to the organizers of this. So, there's Beatrice. Great. Mahesh. Okay, there's James. Wanping, Verena, Soren. Let's see who else is awake. Oh, no, Hongju is there. Okay, terrific. Arpita, of course, Arpita just got up. Okay. Camille, Shrejani, is Diana still awake? Raphael, are you there? You're in California, you should still be awake, okay. Diana's there. Oh, nice. Okay. Petra, are you there? Simeon, are you there? Okay, I guess they are. That is okay. Okay, everybody fixes their hair. Okay. Paul, you're there? I have your photo from last week. Okay, terrific. So I have the excuse, I don't have a camera on this computer. So I don't have to, I can be wearing shorts and a t-shirt, doesn't matter. Okay, so thank you very much, everybody, for presenting. I hope this format worked okay for you. I know it's really crazy late for a lot of you and really crazy early for Arpita. Same thing, right? And so I appreciate that. I'm taking some screen capture. I'm going to send that to Christina and Jingyi, who are at Columbia, and see how we can get this to you. Or I'll just put it on the Twitter feed. But thank you so much. I'm going to put in the clap. I really appreciate everybody. I'll give you a clap in my chat. Oh, there's Sinead. They're all waving. I think she can hear. There's Sinead up there. Yes, I don't know who else is there. But I hope this worked. I hope you feel like you found some new research you're interested in and that other people approach you about your research. I did want to, okay, great. I got screen capture. So if you feel sleepy, you don't have to keep on pretending to smile. Okay. So last week, I'll just have a few announcements. We had our U.S. Africa Initiative workshop. I put the link there in case you're interested. We had some talks. They were all live. We live streamed them and on the YouTube channel. And I made this huge list of all of the talks that we had. They're all recorded there as well as in video. So I'm going to put this very long list of talks in the chat, just so you can get an idea of everything. Let's see, how do I put that in here? Paste. Oh, maybe it's too long. Okay. Okay. Let's see. Yes. Okay. Just to give you an idea of some of the things that we talked about last week. And so these are all online. I have links to all of the videos that people submitted. And I'm going to put my name and email in the chat again. So there were quite a lot of things. I know some of the topics might have overlapped with some of what you had going on tonight. And we also had, in addition to some of the opportunities I'd mentioned for some, electronic structure connections, specifically between US and Africa, but also many other nations, there's some, workshops and summer schools and other opportunities to present your work. We did have a science communication workshop by Matteo Rini, who's an editor at the APS, and he also has a link there to a previous talk he gave, but he took questions and answers at that session. And again, I am helping out with this electronic structure meeting. And so that's me, Amy Young. I put in the chat at illinois.edu, and I also answered the US Africa Initiative at gmail.com. And we had a few presenters who weren't here. Jean-Baptiste Fancam, we didn't see tonight, and that's, I know it's very late for him. Not everybody can make it. And of course, Haley Petrus, also at the University of Illinois, was not feeling well, so she couldn't join either. But I really appreciate all your time, and I'm going to go ahead and play Haley's poster now. You have my contact information. If for whatever reason you can't find somebody at this meeting and you would like to get in contact with them, just email me. I'm always happy to put people in contact with each other. You can see in the background the poster sessions are still going on, but I'm going to go ahead and play Haley's poster. I'm going to put the link into the chat and I'm going to play it, and I believe it's a 3-minute. Yes, and after I play Haley's poster, then I'm going to call Jingyi, and she's probably going to have you participate live on the floor. I don't know if you see the grid, but she's got 2 cameras, one on the balcony and one on the floor, and I think she's literally running around looking at the posters. So I'm going to play Haley's poster because she would get an opportunity if she weren't sick today, and then after that I'm going to turn it over to Jingyi's on the floor cam. So I hope that will be okay for everybody. And let me just get this YouTube link here from Haley's. Okay. Okay. And I'm also going to give you, it's got a time code because I already watched part of it. But okay, that's in the YouTube. And if you can't access YouTube, then I will go ahead and play it right now. And it's about 3 minutes exactly. All right. Okay. Let me share my screen. And then I have to also share the sound. Yeah. So you can see I've been looking at a lot of cooking recipes because my shepherd's pie is in the queue. Okay. So let's play.
Today I will be presenting. My name is Haley Petrus, and I am a 4th-year graduate student in James Shepherd's research group at the University of Iowa. Today I will be presenting data on the dissociation of diatomic molecules at finite electronic temperature. We are interested in modeling the potential energy curves of diatomic molecules to measure the effect of temperature and bond stretching on strong correlation in these systems. This is well understood in the ground state, and we are interested in how these change with temperature. Diatomics are also of interest because they can represent different chemical and physical environments. Density matrix quantum Monte Carlo is an ideal candidate to study strong correlation because of its ability to describe complicated electronic structure through the density matrix. In this work, we begin with the finite temperature variation of full configuration interaction, FTFCI, where we perform a sum over states with the entire FCI spectrum. We will also use the initiator piecewise interaction picture DMQMC method. Using FTFCI, we find that the first row diatomics share a set of qualitative features in the STO3G basis set. At low temperatures, curves compare well to FCI. When the temperature is increased, we find that there is a barrier to dissociation. For the later diatomics, we find that the curve is completely repulsive at intermediate temperatures. But then as the temperatures increase to an extremely high temperature, we find that a second shallower and wider bonding well exists for all the diatomics. We can then take these curves and use a quadratic interpolation using the 3 points nearest the minimum to obtain a harmonic-like approximation and take the second derivative at the minimum to estimate the force constant. We find that in general, the force constant decreases with increasing temperature. We can also look at the estimated equilibrium bond lengths, and we see a two-phase plot where at low temperatures a shorter bond is favored and at high temperatures a longer bond is favored. Looking at the continuous spectrum of dissociation energy, we see that it starts non-zero at low temperature, then decreases with increasing temperature, before increasing again at extremely high temperature. Finally, we show that we can go beyond FCI by using initiator PIP DMQMC. We find that the N2 CCPV-DZ data has similar qualitative features to that obtained with STO3G and FCI. One of the more important parts of this investigation is our study of the population distribution across the density matrix as a function of both bond length and temperature. We find that there are more elements in the stretched bond length than the equilibrium bond length that have similar weights to the Hartree-Fock element. This means the system has more multi-configurational character and will be more difficult to resolve the energy accurately. When we increase temperature, the population distribution for both of the bond lengths becomes more evenly distributed. We are currently writing up this work, and we would be happy to take questions via email. Thank you to the Department of Energy for funding and NERSC for additional compute time.
Okie dokie. Thank you, everybody. So let's see. Oh, Cyrus. Cyrus is here. Great. So Cyrus, we're ending now. You see there's Jingyi there. I don't know if she can hear me. She might not be paying attention to me. But I'm going to, of course, happy to do it. So, all right, I'm going to turn it over to Jingyi if she looks over here. I'm sending her in the chat, like, look over here. Okay, so she's not paying attention to me. Okay, I feel that we had a good poster session. I hope you do too. We don't have any other people who are presenting, so I'll just let Jingyi take it away. I might have to call her on a cell phone so she looks over here. Okay. All right. So hang out, and as soon as I can get Jingyi's attention, then Jingyi, talk. Oh. Okay. Unmute.
Hi, Amy. Here we are a little bit noisy. Hi.
Hello.
Hi there. Hi, Olugbenga. Is that Olugbenga? It's very dithery. Yeah.
Oh, she's not showing a video, but she's talking.
Can you see me or can you hear me? Hi, Olugbenga.
Oh,
Is that Olugbenga?
Hi, Amy.
How are you?
Fine, thank you.
How's New York going?
New York is fine. I enjoy it.
We had a nice poster session here, Jingyi. I have to see how many people, but I think we had 14, 17 posters. So that was great.
Yeah,
yes.
That's a lot of posters. Thank you all so much for holding this virtual Zoom meeting. That's so important. I have that live stream that I said in the chat, so we will go back to see that later.
Okay.
And I was wondering.
She has this little camera with a microphone on it, so she'll actually walk with the camera over to whatever poster you want to see. So if you want to see something, you just unmute yourself and tell Jingyi, or you can type it in the chat, and she will pick up the camera for you and walk over to that person. So we've never tried this before either. So we're trying all of these new things today. Yeah.
Also, I mean, since it's already like 9 p.m., I think it's
Yeah.
if people want to, if you want to leave, you can leave if it's okay for your session. So.
Oh yeah, yeah.
we can
Everybody
also hang out here.
presented who's here. Yes. So
Yeah.
if it's just
So-
if you are a virtual participant and you'd like to Jingyi, do you like to walk around with Jingyi? Please say so. And but if you're tired and it's 3 a.m., 4 a.m. or 1 a.m., of course go to bed. Yeah. Hi Keely, how are you? Hey Beatrice, bye-bye, good night.
Bye, good night.
Bye-bye. Great. So, okay, Jingyi, you're going to stay with the camera? Jingyi? No,
Can you hear me?
Jingyi, don't go. Yeah, don't go. Can you carry the camera around? Can you carry the camera around? Just walk around so people can see what's going on.
Okay. 1 second, please.
Okay.
Checking.
We never tried this
Hope
before, so we just wanted to try it.
This is kind of. Oh, we are in the second shift, so it's like the poster numbers with larger than 20 is still here. So hopefully this works for you. Let me see if this deck works. Okay, can you see my camera now?
Yeah, I see the tabletop. Yeah, can you walk around and just show us the posters?
Sure. So I hope this won't frighten the people who is still talking. So okay, I'm going to yeah, a little bit noisy. Just okay, bear me. Okay,
Ah, nice.
Can you see?
Is that Tina? Yeah, from University of Iowa.
Yes. You want to see something to the Zoom virtual poster? Just these are Zoom presenters. You want to like?
You can listen to the rest of my spiel. I should give it a spiel. So we actually, this results right here, we show that we can reverse the separate results of FFT and we can run the previous method of numbering. So our next step was then to try it on real systems. So this is a model system, this is a real system. Here, we ran a range of metals, insulator.
To walk around. If you are interested in anyone, just let me know. Okay, so this is Fan Chen Long's poster. I'm going to put it really close for you to see the details.
Oh,
if
good.
you're interested in this present, yeah, just let me know. Let me know. So I think the presenter is currently not here, and here we saw Yeti Fauna. Hi, hi, Yeti Fauna. Hi, would you? Sorry to interrupt, but hi. Let me do this here. So, hi, Amy, can you hear?
Yeah,
Okay.
Hi, Yedofana. How are you?
I'm fine.
Virtual Zoom meeting. So, they're just Yetifana and Olubanga was talking about the poster. So, you can just continue. Just,
Yes.
Yeah, just continue.
I'm explaining my work. It's a charge transport study on lithium air and lithium-ion and sodium-ion batteries. And as you can see, the charge transport in the bulk and charge transport in different surfaces. And actually, in addition to surface and bulk, we also calculate the charge transport in the interface, the cathode electrolyte interface, and we see some results. And as you can see, maybe here in a lithium air battery, the interface is normally constructed from lithium peroxide and lithium carbonate. Lithium peroxide is the main discharge product in lithium oxygen batteries, whereas the lithium carbonate is a side product. Okay, this carbonate normally potentially originate from the electrolyte decomposition, or it could be from the graphite decomposition, or maybe it could also maybe from the air contamination. So there are three scenarios of the formation of lithium carbonate. So we build the interface between lithium peroxide and lithium carbonate in a lithium battery. the sodium air battery, we have a sodium superoxide as the main discharge product and sodium carbonate as the side product. So probably we'll have sodium superoxide on top of sodium carbonate. This is our interface, and we study how the sodium ion is moving across this interface in all the three directions, in X, in Y, and Z, and present this graph. As you can see, this barrier is less than 0.4, which means the ions or the sodium ions can easily move from one initial point to the other with this energy barrier. So the same is true for lithium peroxide and the lithium carbonate. As you can see, you cannot see any barrier, only the thermodynamic barrier. That is mostly, this one is the most stable when the vacancy is on the carbonate part of the interface. So this is for lithium air, that one is for sodium air. And on top here you see, this is the charge transport study and the bulk of lithium manganese silicate. As you can see, all of them is micro around 0.8, and this one is even beyond 1 electron-volt. That means the ions are moving in a limited condition. But when you come to the surface and when you apply biaxial strain, you can see that it's less than 0.4 energy barrier. Here is less than 0.55, which means by applying the strain and by forming the surface, you can improve the conductivity of this cathode battery material. Thank you very much. If you have questions, you are welcome.
Yeah, if you have questions, you are welcome.
Okay, thank you. Thanks, Yerofana. I put your name and the name of your poster in our chat. Okay, Jingyi, we're ready to go to somebody else.
Here is Garu's poster, but Garu is not here. So hopefully we will find him somewhere else at people's posters so we can see. And here we go to Google. I'm not trying to disturb, just they're already talking.
Yeah.
Thank you so much. I'm just trying to like sneak in and give a closer view. Hi Google, this is Amy.
Hi, where's Amy?
Oh, Amy.
Hey there.
Okay.
How are you?
Good, thank you. How was the poster session today?
Oh my gosh, it's amazing. I'm having fun. I'm having fun explaining experimental work to theoreticians.
Oh yeah, exactly. It looks like today we're having a lot of theoretical people.
Yes.
Yeah.
And with us, we don't really do theoretical work. Yeah. So this is a new, new environment for me.
Oh, new, yeah.
Yes. Yeah.
How do you feel like?
I mean, looking at all those equations, definitely you're slightly out of your depth. Well, for me, but because some of my work actually I built on it from DFT observations.
Oh.
So we don't just go on from it as an independent thing. We read up a lot on the findings from DFT and try and see if we can observe similar things experimentally, which is what we did there. So we've read a lot on DFT work. What have they found there? How do they explain the conductivity mechanism of these materials and see if we can apply those experimentally and how well do they agree?
Yeah, that is so good.
Thank you so much.
So it's like new area, but not so new.
Yeah, it's new, but not really that new. So it's interesting to see everyone working from a perspective of theory and needing to validate those theories by experiment.
Yeah.
Whereas with us, we're working from experiment and working backwards essentially.
That's important.
Yes.
Thank you so much.
Thank you so much.
So I'm walking around to the next spot. So here people are already talking.
Gives us, 8 million data points that we train on, right? So
I'm just going to walk around. Here is another poster, but people is not here. I think because that's already a very long night. People are just getting some drinks, and we are having other posters here.
How's everybody feeling on the Zoom chat? Are you ready to say goodnight? I think some people are a little bit tired.
Hi. Do you want to like say hi to Amy?
Hi, Amy.
Hi, Amy.
Hi,
Can you hear
Anwumi.
How are you?
Yes, can I hear? Can you hear me? Hi, Adewumi.
Yeah,
It's so good to see you.
hold that for a while? Yeah, I'm going. Sorry, I'm going to make this louder. So how about it now? Amy, can you hear me?
Yeah, I can hear you fine. Can you hear me? Hi, Adewumi. It's so good to see you.
Hello, Amy. Hi, it's good to see you. How are you?
I'm good, thank you.
Yeah.
How was the poster today?
How was the poster today?
Yeah, not bad. It was good.
Excellent.
So you've done the calculations for all those 44
Yeah.
structures
Yeah.
for different
I did
combinations.
for
Wow.
three. Because this is the parent material, calcium monoxide.
Ah.
So I induced the carbon there. I induced it with chromium. Yeah, in order to find out, because our interest is to check whether that mixture will be applicable for spectronics devices. So when we did that, we discovered that for the 25% chromium in terbium, that structure will not be stable. But for the 50 and the 75, we discovered that they will be quite good for spectronics application.
Wow.
Jingyi, can you hear me?
Yeah, I can hear you.
Okay, I think everybody here is sleepy.
Yeah, so I think maybe I just quickly show, just doing a very quick show, really quick.
I think, yeah, just do one last second and then I think everybody wants to go tonight. It's 2 a.m., 4 a.m. Yep. Okay, bye. Demorai. Oh, that's Jingyi's poster. And bye, Mahesh.
Poster as well, and yeah, I'm having a lot. So
Okay.
I think here is all the posters we are having today. So if you
Looks
are
great.
already like tired, just okay.
I
it's
think
okay to
everybody
go.
here is pretty much tired.
Yeah, I think we can. I'm sharing the screen here, so you can see all of you here.
Yes.
Thank you all so
Okay.
much. Yeah, thank you
Okay.
all so much.
Okay.
This meeting room is wonderful.
It looks great. Jingyi, I did take a Zoom group photo, so I'll email that to you tomorrow, okay?
Okay, great. Thank you so much. Thank you so much.
Okay.
Okay.
I'll send you some email. Okay, good night.
Goodbye. Good night. I will hang on this for a while. Just feel free to go.
Okay, I'm gonna
See you.
sign
Thank you.
off so I can prepare for tomorrow. Okay. Good night, everybody. Bye, James. Okay. And bye, Dr. Jerome.
I'm going to see this. Bye.
Recording stopped.